So hello everyone, welcome to another segment on supplementary video series. So in the last session we were discussing about the basic idea of eigenvalue problem. So we were able to establish what do we mean by an eigenvalue. So we were discussing about eigenvalues, eigenvalues and eigenfunctions of our operator, and we showed an example of the second derivative operator and showed how the trigonometric functions, like for example here you see the f1 sine alpha x and cos x were the eigenfunctions for the second derivative operator. Okay, so we will be discussing another important property of various kinds of in specifically to quantum mechanics, and that is the idea of Hermitian operators. So that's the topic of this segment. So we will be discussing about Hermitian operators. Okay. So what do we mean by Hermitian operators? So the definition is, so an operator A hat, let's say, is Hermitian if it satisfies the following definition. If it satisfies the following definition. Satisfies the following property. So let's write down that property. That is, so let's say we want to test whether the operator A hat is Hermitian. Then if it is Hermitian, then it should satisfy the property the integral of G star times A hat f d tau should be equal to the integral of A hat G the whole conjugate f d tau. Okay, so here remember we are testing for whether A hat is Hermitian or not. Okay, so A hat is the operator that we are testing for, and f and g are arbitrary functions. Okay, and d tau is the appropriate volume element. Okay, volume element is less measure that depends on the dimensionality and the coordinate system used. So this depends on the dimensionality coordinate system use. Coordinate system use. Okay, so that's the generic identity that an Hermitian operator should satisfy. Okay, so remember here, like in general, the functions f and g are general and could be complex functions. Okay, so that's a very important thing, because you will see that is the reason Hermitian operators are so useful in quantum mechanics, because you will see these eigenfunctions are inherently complex, and the wave function specifically, like you will be seeing, it's a complex valued function in general. Okay, so that's the generic idea of what we are meaning by a Hermitian operator A, where one thing we need to keep in mind, this means complex conjugation. Okay, conjugation, complex conjugation, So that means, let's say we have a complex number z, which is x plus iy. The conjugate z star is defined as x minus iy. So that's what we mean by complex conjugation. Okay. Same thing, like it's valid for any function. Okay. So let's use this definition and see whether, let's check for some operators whether they are Hermitian or not. Okay. So for example, let's check whether the first derivative operator, let's say the ddx is Hermitian or not. Okay, check whether ddx is Hermitian or not. So how will we do that? So let's apply the definition of an Hermitian operator. So let's say that's g star a f d tau is a g whole complex conjugate f d tau. Okay, and this is, and for our specific example here, a hat is the derivative operator ddx. Okay, so let's see. So let's apply. So let's take the left hand side of this thing. So the LHS, that the LHS becomes the integral of g star dd df dx. Okay, and let's do it in one dimension. So d tau becomes just dx. Okay, so that is the LHS. And so let us do one very important thing, and that is, let's keep in mind, let's write what is ddx of g star times f. Okay, and we can use the product rule to write this thing down. So this is g star df dx plus f dg star dx. Okay, and you see here we have g star df dx, here we have g star df dx. So let's make that, let's take that out and write it in terms of this. Okay, so let's write that g star df dx, that becomes ddx of g star f minus f dg star dx. Okay, so then using this thing, using this here, the left hand side becomes the integral of ddx g star f minus f dg star dx. Okay, all multiplied by dx. This becomes the integral of ddx of g star f dx minus the integral f dg star dx. Okay, so one very important thing about the functions that we did, so normally these functions f and g, normally the functions f and g vanish at the boundaries. Okay, so therefore you will see this term goes to 0, because this becomes just g star f at the boundaries. So let's call, and let's say this is integrated between 2 points 1 and 2, and that is the boundary. Let's say that is the domain boundary. This is the point 1, 2. This is like, let's call that x1 and x2. So at these 2 points, the functions themselves has to vanish. So f of x1 has to be 0, f of x2 has to be 0. Okay, similarly for g. Okay, so this is like 1.1 to 2 minus the integral f 1 to 2 dg star dx. Okay, so using the idea that this function f and g vanishes at the boundary, this term goes to 0. This term goes to 0, so we are just left with, so the left hand side becomes minus integral f dg star dx. Okay, so that's the left hand side. Let's write down the right hand side. The right hand side, if you see, is the integral of a, the operator, which is ddx. Okay, and if you see, it's a g star dx, f dx. If you see, this is what is the right hand side, where we are using a one dimensional, so d tau is dx. So this becomes, if you see, this becomes integral f dg star dx, and you see LHS is not equal to RHS, as you can see, because you see the LHS is, you have a positive sign here, you see, and if you see the left hand side, the left hand side is negative, as you can see, because the underlying term is the same, but if you see there is a difference in sign. Hence the derivative operator, the first derivative operator ddx, is not an Hermitian operator, you see. So therefore we prove that ddx is not a Hermitian operator. Hermitian operator. Okay. What about other operators? Let's say we have another example where we have operator I, where this is I ddx, but this I is the imaginary number. Okay, so this is square root of -1. What about this? Is this entire operator, is this Hermitian? We'll see this is Hermitian. This is an Hermitian operator. And if you do the same procedure, we can check that will become Hermitian. How can you see that? So if you see, the left hand side will just become, if I will just skip the steps, but I'll just write the LHS. So the LHS will become minus, just like before, nothing changes. So it will become minus integral minus I integral f dg star dx. Okay, that's the left hand side, because now you remember that the operator is I ddx, so therefore you will know an extra I factor. Okay, and the right hand side will become the integral of I dx of g complex conjugate multiplied by f dx. And now if you see, when we do the complex conjugation, so I complex conjugate is minus I, if you see. So this will become minus I integral f dg star dx. So therefore you see here LHS becomes equals to RHS. Okay, LHS is equal to RHS, and hence we show that ID, therefore I dx is Hermitian. Okay, so that's the basic idea about what do we mean by Hermitian operators. Similarly, we can show, let's say the operator, the second derivative operator d2 dx2 is also a Hermitian operator. So Hermitian operator. Okay, and this you can test it yourself, test it out just by looking at this expression. You will see now we have to do this. So this is, if you think about this step that we did, this was basically integration by paths in disguise, and we have to do this twice, so we will pull an extra minus. So that minus sign will be absorbed. So when we'll compare the LHS and RHS, both will be now positive, and hence we can show that this second derivative operator will be an Hermitian operator. Okay, that's a very important operator that will be used in quantum mechanics, because in general in quantum mechanics Hermitian operators are related to observables that we measure in lab, that we can measure, or let's say that we the objects that we can measure basically. So we will see that the eigenvalues of Hermitian operators are the measurables. Okay, so I will write it down here. The eigenvalues of Hermitian operators are the observables of quantum mechanics. Okay, and this follows from a very important fact that we will just see. There are some very interesting properties of Hermitian operators. I will write that down. The properties of Hermitian operators. Okay. Okay, so let's now study some of the properties of Hermitian operators in general. So one of the very important and fundamental property of Hermitian operators are the eigenvalues of a Hermitian operator are real. Okay, so that's a very important property of Hermitian operators. Okay, and let's see how can we prove this thing. That's a very simple proof. Let's do it. So let's say so you want to understand the eigenvalues of a Hermitian operator. That means the Hermitian operator should pose a eigenvalue problem. So let's write the eigenvalue problem first. So that is, let's say an operator acting on a function f gives us scalar multiplier of the function f. Okay, so here f is the eigenfunction and a is the eigenvalue. So this is the eigenvalue equation. Okay, this is the eigenvalue equation. Okay, and then what we have to prove is, the equivalent mathematical statement of this is that we have to prove that a is the same as a star. That means a is real. A is a real. Okay, it's not complex. It's not a complex number. It's a purely real number. So a number whose complex conjugate is same as the number itself, that's a real number. Okay, so we know that a is Hermitian, correct? So we know a is Hermitian. That is, the integral f star a f d tau should be equal to integral of a f star f d tau. So we just use the definition of an Hermitian operator. So this could be rewritten as, instead of af, remember this is the operator. Yes, instead of af we will be substituting this because it satisfies the eigenvalue equation. So this becomes f star af d tau equals, and instead of that we will again write a f becomes af whole star f d tau. This becomes then a star, okay, integral of f star f d tau. You see, if you compare this and this, okay, so this becomes a integral f star f d tau is same as a star integral f star f d tau. Okay, so that means a minus a star integral f star f d tau equals 0. So in general, this will not be equal to 0. Is not equal to 0. We'll see later why. So this has to be equal to 0. Has to be equal to 0. So that is a equals a star. Okay, so for any arbitrary function, you see f, where not arbitrary I will say, because this is an eigenfunction. So this is an eigenfunction for the operator a. Eigenfunction operator a, the eigenvalues are real, as you can see. So that's a very important property of Hermitian operators. Eigenvalues of Hermitian operators are always real. Okay, and that comes to the second property, second important property, associated eigenfunctions. Eigenfunctions form a complete orthogonal and normalizable set. Okay, and part of this proof is here, where when we said so for that, let's so we'll say, so let's do this like this. So if the integral of, say, g star f d tau equals 0, and the integral of, say, f star f d tau, this is not equal to 0, we'll see. Okay, so then f and g are orthogonal. Okay, one important thing you realize here, that when you multiply a function by its complex conjugate, this is always a real number. This is a real positive quantity. Okay, so if f is not equal to 0, f star f is always positive. Okay, you can think about from complex analysis, like let's say we have z is x plus iy and z star is x minus iy, then the product z star is x plus iy minus x, so this just becomes x squared plus y squared. As you can see, this is a positive number. It's always positive. Okay, this is mod z squared basically. Okay, so therefore this is never equal to 0, as you saw here. Okay, and using that idea and this idea, we can say when two functions are orthogonal. Okay, so let's see how we can tell whether if we have an Hermitian operator, the eigenfunctions of the Hermitian operator will be orthogonal. Okay, So let's say you have A acting on the function f, it should provide S times f. It's an eigenvalue problem, correct? And so that's f is one of the eigenfunction, and let's say we have another eigenfunction, let's say that, let's call that g, and it acts on to provide another eigenvalue times the eigenfunction g. Okay, and if you see, if s is not the same as t, that means these two are different eigenvalues, then what we need to show is the integral g star f d tau has to be equal to 0. Okay, so that is the orthogonality condition. Okay, and again, like the easiest way to do is just by applying the definition of Hermitian operators. Let's do that. So the integral of f star a g d tau is equal to integral a hat f star g tau. Okay, and this can be rewritten as, if you think about just by using that, a hat g is tg and a hat f is sf. If we just use that substitution, this will become the integral or let's write it in a little bit. Let's rewrite this in a different form, because what we want to show here is g star, not f star. So it will just slightly change the way we write the Hermitian operator. It's one and the same. So that will be g star a f d tau is equal to integral of a star g, or a hat g whole star f d tau. Okay, so that's this statement is the same as basically this statement. There is no difference, just the way how we are casting it to prove actually. So since here we want g star, that's why we want to keep g star here. That's why we are using this definition for writing the Hermitian operator definition. Okay, so now we'll just use the identity that we already have, which is a hat f is sf and a hat g is tg. So that will become integral g star sf. Okay, so instead of af, sf, and this becomes d tau, and that is equal to integral a star g. Instead of that, we'll write tg whole star, that becomes f d tau, and then this becomes t star integral g star f d tau. And since this is an eigenvalue problem, we know that t is real from the previous property of Hermitian operator, and we know that a is an Hermitian operator, therefore t star is the same as t. So this becomes just t integral g star f d tau. So therefore what we have is s minus t integral g star f d tau equals 0. And since we already told that s is not equal to, that means this is not equal to 0, this is not equal to 0, so the only way this can be 0 is this is to be 0. Okay, so therefore this implies that integral g star f d tau is 0, and hence we prove that f and g are orthogonal. Okay, so f and g were the two eigenfunctions of the Hermitian operator, and then we showed using just the definition of Hermitian operators that f and g has to be orthogonal. Okay. That's a generic idea of Hermitian operators, and Hermitian operators are very much useful in specifically in quantum mechanics, because as we discussed before, it like the eigenvalues of the Hermitian operators are the quantum mechanical observables. Okay, so I think so that's what this segment was all about. So we discussed about Hermitian operators, what are Hermitian operators, and we saw two important properties of Hermitian operators: that the eigenvalues of a Hermitian operator are always real, and the associated eigenfunctions forms a complete orthogonal basis set. And if it is orthogonal, we can easily show it's normalizable. It's just a matter of scaling. That's what normalizable means. Okay, so I think so that's for this segment. Thank you for listening. Okay, so we'll see you in the next segment. Thank you.